All right. Welcome everybody to this webinar series on Beyond Diagonal Reconfigurable Intelligent Surfaces, organized by the Special Interest Group on BD-RIS. My name is Matteo Nerini. I am the secretary of the Special Interest Group. And today is my great pleasure to host the second webinar of the series. Today we have Dr. Philipp del Hougne from the University of Rennes in France. Let me briefly introduce his biography before giving him the floor. Philipp del Hougne is a tenured CNRS associate professor affiliated with the University of Rennes in France. He graduated in physics from Imperial College London in the UK and received a PhD in physics from the Université Sorbonne Paris Cité in France. He then held postdoctoral positions in Nice and Rennes and Lausanne in Switzerland. In 2023, he received the Habilitation à diriger de recherche degree in electronics from the Université de Rennes in France. He currently leads the Intelligent Wave Systems Group at CNRS IETR, Université de Rennes, in France, which studies the theory and applications of tunable complex wave systems to mold the flow of information through tailored wave-matter interactions, spanning applications from information extraction, like imaging, sensing, localization, via information processing, analog wave-based computing, to information transfer, such as in wireless communications. Now, let me briefly remind you the rules of this webinar. The talk will last approximately 50 minutes, during which all the audiences will be muted. And afterwards, there will be a Q&A session when we will pick some questions written in the chat, or some of you can be unmuted to directly ask the questions. So enjoy the talk, and Philipp, the floor is yours.
All right, so hi everybody, and many thanks, Matteo, for the kind introduction and also for the invitation. Let me just see if I can share my screen. Is it already shared? No.
Yes, the PowerPoint, not full screen actually, but we can see the PowerPoint.
Yeah, let me just, because something looks weird, and I'll just share it again. Because I couldn't see it on my computer, but I think now should be better. Now you can see it, right? Full screen.
Yes.
Okay, great. All right, so yeah, many thanks for the invitation. I'm delighted to speak in this webinar series, and I chose a rather broad title to share some of our recent efforts in understanding and exploiting mutual coupling in reconfigurable wave systems. And of course, I think everyone in this webinar series is sort of fundamentally interested in mutual coupling, because the beyond diagonal tunability is fundamentally about tuning coupling. So I'll try to share some of our insights, and many of them are, by the way, not only specific to RIS. That's why I picked a more general title, Reconfigurable Wave Systems. Before I start, I would like to acknowledge my collaborators who contributed to different parts of what I might mention, including, of course, our host. And now, the starting point for our efforts in this area are the realization that the next generation of wave systems will require extreme transfer function tunability. And this applies really to most microwave systems, including antennas, filters, routers, physical neural networks implemented in the wave domain, of course, radio environments, as everyone knows. And so in order to achieve that extreme transfer function tunability, we might have to fundamentally rethink the principles by which we design reconfigurable wave systems on the hardware layer, because currently mutual coupling for the most part is either neglected or mitigated or coarsely approximated. But those approaches might, on the one hand, not work once we're moving to hundreds of tunable degrees of freedom. It might be impossible to mitigate all the mutual coupling and might be inaccurate to just ignore it. And on the other hand, maybe also it might actually be better to exploit it rather than to consider it a nuisance. And of course, we also need to develop matching algorithmic approaches for optimization that match our hardware design principles. So these are coupled problems. And what we've found and what I will show you at the beginning of my presentation is that strong mutual coupling between the tunable elements actually boosts the transfer function tunability. But of course, it also means that the relation of the transfer function and the configuration is more complicated. And so in order to re-app these benefits of strong mutual coupling, we need compact physics-based models that are aware of this mutual coupling and that we can calibrate so that they describe a specific experimentally given system. And then we can use them for optimization. So I'll mostly focus actually on the calibration part. So because this is, by the way, I think also the part that has sort of received the least attention in the signal processing community. So given an experimental reconfigurable wave system, how do we actually find the parameters of our model to describe that specific setup? And related to that, I'll mention a byproduct of our efforts in developing methods for parameter estimation, which is the virtual vector network analyzer that we use to measure large scattering matrices without manual reconnections. And then towards the end, I'll clarify how everything that I talked about thus far can be transposed to beyond diagonal tunability. So to give you an idea of what sorts of reconfigurable wave systems I'm thinking about, of course, the most prominent example are smart radio environments, and I believe everyone in the audience is familiar with the concept of RIS and how that parameterizes wireless channels. Another system that we're very interested in are dynamic metasurface antennas. So this is essentially a very compact hybrid MIMO technology where you have one or a few feeds that excite in this case, a cavity from which waves leak in a programmable manner to the far field. And also we have some interests in reconfigurable signal processing, which could be for reconfigurable filtering, routing, or implementing analog wave-based physical neural networks. So all of these examples look quite different on the surface, but actually conceptually, they're all very closely related because in all cases, we're looking at a linear wave system whose transfer function is parameterized. Whose transfer function is parameterized by a set of tunable parameters. So the transfer function maps the input wavefront X to the output wavefront Y via some transfer function H, and that is parameterized by our system configuration C. And so in principle, there are two sorts of problems we have to think about. The forward problem is what is the transfer function for a given configuration, and then the inverse design problem, what configuration closely approximates a desired transfer function. And so some of the questions that we think about is, first of all, given our aim to achieve extreme transfer function tunability, how do we actually maximize the sensitivity of our transfer function to the configuration? What are the overarching design principles that enable that? And then in terms of optimization, fundamentally, do we prefer a model-based or a model-agnostic optimization? And if it's model-based, then how do we formulate and calibrate a model for a given experimental reconfigurable wave system? So overall, we're trying to understand this trade-off between maximizing sensitivity and the difficulties that it implies in modeling and optimization. And so it is our belief that, in principle, model-based in-software optimization of an experimentally given reconfigurable wave system is ideal, provided that we know how to formulate the model, how to estimate its parameters, and how to efficiently use it for optimization. And the overarching goal of my presentation is to show you that we can actually do all three of these things, including in cases where we have very strong mutual coupling, which turn out to be the ones that maximize the transfer function tunability. So here's the outline of my talk. I'll start off by discussing some general hardware characteristics that maximize transfer function tunability. And then I'll describe how we formulate physics-compliant models, how we estimate their parameters, and here I'll have a digression to discuss ambiguities in the parameter estimation and how that relates to the virtual vector network analyzer concept. I'll say just a very few words about how we can use a calibrated model for optimization. And finally, I'll move on to discussing how we can transpose all of the ideas that I discussed in the first 4 parts to beyond diagonal tunability. So I'll discuss a little bit what is really the difference between diagonal and beyond diagonal, and local versus non-local, and correlated versus uncorrelated tunable variables. And I'll show you our first BD-RIS prototype and also our transposition of that concept to dynamic metasurface antennas. But to start now, I want to think about general hardware characteristics that maximize transfer function tunability. So specifically, I want to explore the impact of the mutual coupling strength on the tunability of the transfer function. And to make that discussion concrete, I will consider a specific reconfigurable wave system, which is this dynamic metasurface antenna that I already mentioned previously. So this is essentially a two-dimensional chaotic cavity defined by 2 parallel plate waveguides and a series of vias that is fed from the back by 1 or multiple feeds that excite the field in the cavity, and that field can leak out through these programmable meta-atoms. And so depending on which of these are switched on or off, we will sort of coherently generate a programmable wavefront. And of course, the same works in reverse also to capture coherently. And this is a convenient system to consider because we have a numerically efficient coupled dipole model for this dynamic metasurface antenna, in which we can tune the mutual coupling strength, and also if we want we can impose a limitation to single scattering. Now what I want to look at is how the mutual coupling strength affects the following 2 aspects. First of all, our ability to tune the radiated field, and I'll quantify this in terms of the sensitivity of the radiated field to the configuration. And secondly, how easy it is for us to predict the radiated field. And I'll quantify this in terms of how accurately a linear regression can predict the radiated field. Now, to start, I want to show you some sensitivity maps. So these are not radiated field patterns. These are the sensitivity of the radiated field to a change in the configuration of 1 meta-atom. Now, if there is no mutual coupling, then the sensitivity map looks like the radiation pattern of a single dipole. And that makes sense because changing the configuration of 1 meta-atom does not induce any changes in the dipole moments of all the other meta-atoms, and that's why it looks like the radiation pattern of a point source. Once we move to systems with more and more mutual coupling, then changing the configuration of 1 meta-atom will also induce changes in the dipole moments of many other meta-atoms due to the mutual coupling. And so the sensitivity map starts to look like the interference pattern of multiple point sources. Now, the intuition here is that the longer a wave bounces between the tunable meta-atoms, the more sensitive the system's transfer function will become to the meta-atom's configuration. But also, the more the impact of 1 meta-atom's configuration on the transfer function will depend on how the other meta-atoms were configured. So there's a fundamental trade-off between the tunability and the simplicity of the mapping from configuration to transfer function. This is exactly what we see in our numerical study. As we increase the mutual coupling strength, we increase the sensitivity of the radiation pattern to the configuration, but at the same time, we reduce the accuracy of a simple linear forward model. So we've also wanted to confirm this in experiments. So we've built a dynamic metasurface antenna. Now, in experiments, it's more difficult to explore different mutual coupling strength because we don't want to fabricate tens of prototypes. So instead, what we do is to adjust the mutual coupling strength in post-processing via time gating. So we essentially measure the radiated field across a wide frequency range. We go to the time domain, and then we truncate this time response at a certain delay time and move back to the frequency domain. And so basically this delay time at which we truncate is a proxy for the mutual coupling strength, because the paths that bounce around in the antenna for too long before exiting are essentially suppressed. And then in our experiments, we observe the dependence of the sensitivity with our proxy for the mutual coupling strength, that is the delay time, as expected. So the longer the delay time at which we truncate, the higher is the sensitivity, and that translates directly into an ability to better control the radiated field, in this case to enhance the gain of a channel in a particular direction. At the same time, we can experimentally estimate the strength of the Hessian, so the second order derivative, and we see that that also increases, and that explains why the accuracy of a simple linear model decreases as the mutual coupling strength increases. So these experimental results confirm exactly the trade-offs that we've seen previously in the numerical results, which is that the more mutual coupling strength we have, the more tunability of the transfer function we have, but the harder it is to actually predict the transfer function for a given configuration. So that's what we've seen so far. And now if we want to actually start to reap the benefits of strong mutual coupling in tunable wave systems, we need adequate techniques to describe and optimize these coupling effects. And so what I want to show you now is how we can formulate a compact model, how we can calibrate that model experimentally, and how we can use it for optimization. Now, I'll move on and start by discussing the formulation of the model. And for that, I'll slightly switch gears and discuss this sort of prototypical problem, which essentially emulates an RIS parameterized wireless channel. So we have a complicated scattering enclosure. It's a rich scattering radio environment, if you like. We have 4 antennas in there that allow us to couple waves into and out of the system. And then here we have the RISs. And these elements, just to make this concrete, are just patch elements with some pin diodes. The exact details actually don't matter for the discussion in this presentation. And now the big question that I want to address is, well, how does the configuration of these programmable meta-atoms map into the scattering matrix between the antennas that we can actually measure? And of course, that is in principle a scarily complicated mapping because of the rich scattering and because of the fact that we don't actually know the exact geometry and material composition of the radio environment. Now, the generic approach for describing this consists in the following, namely to partition our reconfigurable wave system into 3 entities. The first one are the antenna ports that we use to inject and receive waves. The second one are the tunable lumped elements, in our case pin diodes. And the third one are all the static scattering objects. This applies to metallic or dielectric, point-like or extended scattering objects. And of course, it also includes the structural scattering of the antennas and the meta-atoms. So the metallic parts basically that are static in the antenna and the meta-atoms, they're just lumped into this background of static scattering objects. And by the way, I'll get back to this towards the end of my presentation to clarify that this also applies directly to beyond diagonal tunability, even though at first sight this might be surprising. Now, for now, we'll stick with the regular diagonal RIS. And what we'll do here is to interpret the tunable lumped element as a virtual port to the system terminated by a tunable load. And with that interpretation, we're right in the realm of multi-port network theory, where we think of our reconfigurable wave system as a static system with many, many ports, including the antenna ports and the virtual ports that describe the tunable components. And then the virtual ports are connected to a second multi-port system that captures the tunable loads of our programmable metasurface or RIS. And then standard multiport network theory gives us the relation between the measurable scattering matrix and this very big scattering matrix describing all the static scattering objects in our system, as well as the tunable configuration C. And immediately upon inspection of this formula, we see that the mapping from configuration to the scattering matrix is nonlinear. And we can gain more insights into this mapping by rewriting the matrix inverse as an infinite sum of matrix powers, which, by the way, is guaranteed to converge always because all the systems that we consider are passive. And so this infinite series of powers has a very nice interpretation in terms of a multi-bounce path picture of mutual coupling, because essentially the kth term in that series regroups all the paths that encountered the RIS k times. And of course, you can then also write the series out explicitly. And many of the theoretical works in the wireless communications literature essentially use approximate models that are truncated after this first term that depends on the configuration. And so generally that truncation applies the truncation error, whose importance depends on the mutual coupling strength, as we can see from this model. Now, just to remind you of where we're going, so far what I showed you was that generally stronger mutual coupling yields a better transfer function tunability, but it makes the mapping from configuration to transfer function more nonlinear. And we've seen that we can have very compact multiport network theory models that are fully aware of mutual coupling. And by compact, I mean that the number of parameters only depends on the number of antennas and of tunable elements, but it does not depend on the complexity of the static components. So for example, the number of parameters here is the same irrespective of whether we're in free space or in a rich scattering environment. That only influences the details of these coupling coefficients. Now, what we need now in order to make use of this model is to figure out how to calibrate it so that it describes a given experimental system. So that's what we'll see now. Essentially, if we want to use this model in a concrete experiment, we need two ingredients. We need this big scattering matrix that describes all the static components in our system. And we need to know the vector of reflection coefficients that describes our current configuration. Now, the difficulty is that the big scattering matrix that describes all the static components is generally not known, because if you're in a realistic environment, you do not perfectly know the geometry and the material composition. And even if you did, probably running a numerical simulation would be prohibitively costly. And also, we actually do not generally know the vector of reflection coefficients. This might be, so a wireless practitioner might buy the RIS, and so the design might be proprietary and unknown, or maybe the utilized lumped components are not sufficiently documented. So generally, we do not want to assume that we know this big scattering matrix or this vector. Instead, what we know is the control vector that we choose that maps into a vector of reflection coefficients, and then we can measure the resulting measurable scattering matrix. But we do not know the mapping from this control vector to the vector of reflection coefficients, nor do we know the scattering matrix characterizing all the static components. And so what I want to think about now is whether we can estimate a set of model parameters so that we can accurately predict the scattering matrix in our experiment for any given control vector. And I want to emphasize here again, the goal is to apply this multiport network theory model to a given and essentially unknown experimental system. Now, the easiest way to find a set of operationally useful parameters is to perform a gradient descent. So we measure for a set of known but random configurations of the metasurface, we measure the corresponding measurable scattering matrices, and then we just perform a gradient descent to estimate a set of matching parameters. And that works fairly accurately. So here you can see a comparison of measured and predicted scattering coefficients for unseen random RIS configurations. And it works much better than benchmarks such as a linear regression model or a deep learning model. Fundamentally because these benchmarks do not benefit from the strong physical inductive bias of the multiport network theory model. And by the way, this gradient descent estimation of the parameters also works if we're constrained to non-coherent detection. And that again comes from the mathematical structure in the physical model that basically imposes that in order to correctly predict amplitudes, you must also have understood the phase relations. So here you can see comparison of ground truth and predicted scattering coefficients purely based on non-coherent detection, and you can see that the relations between scattering coefficient phases and also their dependence on the metasurface configuration are accurately captured. And so then that enables us to perform coherent control based on a calibrated model. And by coherent control, I mean both choosing the input wavefront X and the structure of the system, here embodied by the RIS configuration C. And we've tested that experimentally for coherent focusing and coherent absorption. And our performance is actually visually not distinguishable from the one that you would have knowing the ground truth. All right. So far, we've actually only cared about correctly predicting the measurable scattering matrix for a given control vector. And because of that, ambiguities in the model parameters didn't matter so far. We just estimated all of the model parameters together, and as long as they correctly predicted the measurable scattering parameters, we were satisfied. Now, in the following, I want to spend some time thinking about these ambiguities, understanding their fundamental structure, and how we can account for them if instead of estimating all parameters at once, we're moving towards a more segmented hybrid parameter estimation. And finally, I want to then think about whether we can sort of sufficiently constrain the parameter estimation problem in order to lift all ambiguities. So let me first of all illustrate a little bit these ambiguities, and to do that, I'll consider the following setup, which is a modular 6-bit RIS prototype. So here I'm taking the interpretation of an RIS element as an antenna whose port is terminated by a tunable load literally. So here's an antenna array, and each antenna is connected to a programmable phase shifter that can basically impose 64 distinct reflection coefficients for the antenna port. They're traced out here and essentially cover a full circle. And now to estimate a set of parameters to predict the channel matrix from these 4 transmitters to these 4 receivers, I use a hybrid estimation technique. I'll skip over the details, but basically I try to do estimate to limit the use of gradient descent by fixing certain parameters based on reference configuration and measurements for configurations that differ just by one entry from the reference configuration, and then the missing parameters still need to be estimated by gradient descent here. And now here what you can see are the estimates of the available load characteristics based on 5 different random seeds of this procedure. And we can see that there are some things in common, so they all run through the origin, which is actually due to the first step in this procedure. They all have this circular structure, which matches exactly the ground truth that we can measure thanks to the modular nature of this prototype. But it's also clear that there are ambiguities. We do not always find the same set of parameters. But operationally, like I mentioned, this does not matter as long as our only goal is to correctly predict the channel matrix. So provided that we have enough measurements to estimate our parameters, we actually achieve very high accuracies on the order of 50 dB with any set of the parameters that I showed earlier. Now, the next step then is to move towards thinking about very large RISs, where, of course, estimating all of the parameters at once at some point will become computationally unfeasible. And so we'll want to segment the parameter estimation in order to make it computationally tractable. And I'll try to not dwell too long on the details here, but basically we divide the RIS elements into groups that are partially overlapping, and then we can uh, perform our parameter estimation in smaller segments while still ensuring that the ambiguities of the different segments are aligned so that overall the parameters that we estimate are sort of harmonized with each other. And so if done correctly, then that actually also yields pretty high accuracies on the order of 40 dB for this large scale RIS. With that, I'll then move on to the last question on ambiguities, which was whether, in principle, we can come up with a set of additional constraints that will allow us to fully lift the ambiguities. And again, I won't go into the mathematical details, but I'll present to you the conclusions, which, by the way, are most easily found based on a closed form parameter estimation. And the conclusions are that we can estimate the big scattering matrix describing all the static components of our reconfigurable wave system fully and without ambiguity, provided that we can terminate the virtual ports with at least 3 distinct and known individual loads, and that we have pairwise coupled loads. Now, you'll notice that neither of these conditions is satisfied by the typical binary RIS that I described earlier, but it's nonetheless interesting to explore these insights further because they're actually of technological relevance in the realm of instrumentation and measurement. In fact, what they reveal is that we can measure an n-port scattering matrix with an NA-port vector network analyzer, where NA can be much smaller than N, without any manual reconnections. And this is essentially what we now refer to as the virtual vector network analyzer. And so those of you who sort of do micro experiments might be familiar with the fact that vector network analyzers usually have few ports, maybe 2, maybe 4, sometimes 8. But if you have a many port system, like say 10, 20 port system, and you need to measure the full 20 by 20 scattering matrix with a say 4-port VNA, then you need to do many manual reconnections, which are take a lot of time and they're very error prone. And so being able to do that without any manual reconnections is potentially very enticing. So here's the general approach. You have a device under test with many ports. A subset of the ports is connected to the vector network analyzer, and these ports are used to inject and receive waves, while all the other ports are connected to a tunable load network, which has 3 individual loads and coupled loads connected to the neighbors. And then, provided that we have properly characterized this tunable load network, we can use the combination of this tunable load network with a VNA as a virtual VNA with these virtual ports to determine the full scattering matrix without any ambiguity. So depending on whether we want to use a closed form or gradient descent approach, we would choose different sets of configurations of our tunable load network. Let me just show you that this actually works very accurately. So this is the very first experiment where we implemented the coupled loads just with a coaxial cable, because you notice that coaxial cable is essentially a 2-port load network, and so that's perfectly fine as a coupled load. And in this specific experiment, we had 8 ports, 4 of which were connected to the VNA, and the other 4 were terminated by the tunable load network. And upon visual inspection, you can see that the recovered parameters very closely match the ground truth. We've also applied this to non-reciprocal systems. So this is a transmission line network with circulators. And again, the approach works very accurately. You can actually hear in this figure, you can barely see the difference between the ground truth and the estimated parameters. And then we've thought about how we can make this approach truly scalable. So to make it scalable, basically you want something that has a small footprint and that is cheap. And so we came up with this printed circuit board that implements exactly the required characteristics of the tunable load network. And again, we tested it and it works perfectly fine. Having established this virtual vector network analyzer technique, we can now extend it also to more complicated problems. So say now our device under test is actually remote, so we cannot connect any of its ports to our vector network analyzer. But what we can do is connect antennas to our device under test to remotely probe its scattering properties over the air. So essentially, this is the over-the-air channel, the over-the-air wireless channel is essentially some sort of fixture that can be very complicated if there's scattering in the wireless channel. And then the question is, well, if we can have a set of antennas via which we inject and receive waves remotely, is there a way for us to unambiguously estimate the scattering properties of this device under test? Now, the answer is that based on the virtual VNA technique, this actually becomes a very simple two-step procedure. So in the first step, we connect these antennas to a known tunable load network, exactly the one from the virtual VNA, and then we can basically characterize this over-the-air fixture with the established virtual VNA technique. And then in the second step, we connect these antennas to the device under test, which means that basically now we measure the scattering properties of the device under test via our over-the-air fixture that we have previously characterized. And then it's just a de-embedding exercise, and de-embedding the over-the-air fixture, knowing its properties, is then a standard procedure. And so if done correctly, as you can see on the left, we actually are able to recover the scattering properties of the device under test fully remotely with very high accuracy. All right, so what I've shown you so far is, first of all, I argued why we want strong mutual coupling. Then I showed you how we formulate a model aware of that mutual coupling and how we calibrate that model to a given experimental system. And I had a rather large digression about ambiguities in the parameters. But now I want to get back to the main track of my presentation, and because ultimately the goal of formulating and calibrating a model is to use it for optimization. And on this, I will be very brief because it's essentially a signal processing audience which has a lot of experience in optimization. And I guess I'll just say a few words on some ideas that we've had for using these physics-compliant models efficiently for optimization. The first concern that one may have is that this matrix inversion can be computationally very costly when the number of tunable degrees of freedom is large. Now, if the optimization procedure relies on many forward evaluations, as is the case in coordinate descent or dictionary search, then actually we can alleviate the cost of this matrix inversion by updating previous evaluations rather than starting from scratch every time. This is the Woodbury identity, which is quite known in linear algebra, of course. If we're more interested in gradient descent-based optimization, then of course that is possible because this model is differentiable and it can be integrated into all sorts of differentiable optimization schemes. So I want to show you one example here where we used the dynamic metasurface antenna for computational imaging. And our goal was to optimize this dynamic metasurface antenna end to end so that basically our measurements are aware of the task that we have. So we took this physical model and we integrated it into a pipeline together with a digital backend, and then we jointly optimize the physical parameters and the digital parameters. What that does is that the measurement becomes task aware. And so basically the measurement is simultaneously an over-the-air computation of some kind. And the last thing I'll mention is that, of course, we also know the gradients in closed form. And now in the remaining time, I will say a few words about how everything that I've described so far can be transposed to beyond diagonal tunability. And actually, I want to spend some time thinking about what beyond diagonal tunability really means. And I assume that the audience has some level of familiarity, of course, with the beyond diagonal tunability concept, given this is the BD-RIS seminar series. Now, what I want to discuss is to what extent the beyond diagonal programmability is fundamentally beyond diagonal, or whether there's actually a diagonal way of thinking about it. And the key point, I guess, is that the realization of a beyond diagonal load circuit, no matter the architectural details, always, in the microwave regime at least, will rely on tunable lumped elements. And so that means any such load circuit can fundamentally be partitioned into static components and tunable lumped elements. And so then actually, when we're talking about a BD-RIS parameterized wireless channel, we're looking at a cascade of 3 multiport systems. So here's our radio environment, and then it's connected to our BD-RIS, which itself I've partitioned into static components, which would be, for example, wires connecting loads, and the individual tunable loads corresponding to the lumped elements such as pin diodes. And so then, given this connection of 3 multiport systems, we have fundamentally 2 choices of perspective for interpreting this. So I'll start with the conventional perspective, which consists in connecting the static components of the load circuit with the tunable ones. And then, of course, we get a tunable, beyond diagonal tunable load circuit, which I call L here, that is characterized by some scattering matrix SL, whose off-diagonal entries are tunable. And that's precisely what the beyond diagonal tunability refers to. What is important to notice, though, is that with this sort of very hardware-aware perspective, we realize that the tunable entries of SL are correlated. So generally, all entries of this SL are tunable, or potentially tunable, but they cannot be tuned independently. Whereas if we take an alternative perspective by which we first connect the radio environment to the static components and then have the connection to the individual loads, then we end up with a diagonal perspective because we have some big scattering matrix describing static components that is connected to a load network whose scattering matrix is purely diagonal. And the nice thing is that in this alternative diagonal perspective, the tunable entries of SIL, they're all uncorrelated, and that's very convenient for optimization, of course. And the other interesting thing is that because there is always this diagonal perspective for a beyond diagonal system, then we can actually basically recycle algorithms that we've developed for diagonal systems as long as they were mutual coupling aware. So the first attempt in that direction was to use the multiport network theory parameter estimation technique that I described earlier and to apply it to a wireless channel parameterized by a beyond diagonal RIS. So this is a sort of a hybrid experimental numerical analysis here where we have an experimentally grounded scattering matrix describing all the static components, and then we connect it to an idealized BD-RIS load circuit where we choose the properties of the loads depending on the datasheet of a given pin diode. And so we apply exactly the same parameter estimation algorithm that I described previously for the diagonal RIS. And so we see, first of all, here the ambiguities in the parameters, because again, here we just have two possible states for each tunable lumped element, so there are fundamental ambiguities, but operationally, we always correctly predict the end-to-end channel. And when we perform optimization here, it's a small scale problem, so we can actually have an exhaustive search as well. And then we find that based on our diagonal model whose parameters we estimated based on the diagonal algorithm, we find the globally best configuration of the BD-RIS. Now, this was sort of just semi-experimental, semi-numerical. We then wanted to also actually implement sort of a fully experimental beyond diagonal RIS. And so here you might recognize the tunable load network that I mentioned earlier, which actually happens to implement the properties of a specific type of architecture of beyond diagonal RIS, which is a tri-diagonal RIS. And this is a modular BD-RIS prototype in the sense that, like I mentioned earlier, again, we're taking the interpretation of an RIS element as an antenna whose port is terminated by a, in this case, tunable load network, literally. So here we have our antenna array, and the antennas are connected to this tunable load network. And of course, this is not the most compact design, but it's somewhat ideal for academic research because we can actually access the ports of the two systems that we're connecting in our system model. At least in principle, because in practice, this is still a, I think, 15 or 16 port system, and we only have an 8-port VNA. So in practice, we actually use the virtual VNA technique to estimate the scattering matrix of all the static components. And here are just some of the scattering characteristics of the tunable load network and this rich scattering wireless channel. And well, in the interest of time, I think I'll try to go quick. We've evaluated the performance of this BD-RIS experimentally, first of all, assuming ideal hardware and then different hardware constraints that correspond more and more to the tunable load network that we have for different performance indicators. Maybe the two key takeaways are, first of all, it seems that the benefits of having these tunable interelement connections are fundamentally related to hardware constraints. So the less constrained the hardware is, the more we benefit from the tunable connections. And also, with this sort of very hardware-aware perspective, we notice that there are unexplored trade-offs. For example, we're using 5-way switches here, and 2 of the 5 switches are dedicated to establishing the inter-element couplings. We could, of course, instead have 2 more additional loads and have a diagonal RIS with 5 states. And so there's some unexplored trade-offs here in terms of, given such hardware constraints, what is actually more yielding better performance. And now, just before I wrap up, I'll briefly show you that we've also transposed the concept of beyond diagonal tunability from RIS to DMAs. So this, just as a reminder, is the dynamic metasurface antenna I talked about earlier, where each of the programmable meta-atoms is parameterized by a tunable load network, but the intrinsic coupling between these meta-atoms is static because it's just imposed by static components such as the parallel plate waveguides and the vias. Now, to have tunable intrinsic coupling between these meta-atoms, basically we just add tunable vias into that cavity. And then we can think of the beyond diagonal dynamic metasurface antenna basically like a beyond diagonal RIS combined with a feed antenna. Conceptually, that's the same if you have a base station application in mind. But of course, the beyond diagonal DMA is much more compact compared to a BD-RIS if you take into account all the volume that you need to add the feed antennas. And yeah, maybe I'll just mention that in terms of performance, we observe what has been observed for BD-RIS by other groups, including our host, is that the benefits of the beyond diagonal tunability increase with the mutual coupling strength, and I guess this is expected. So with that, I'll wrap up. So the key points that I hope I got across was that, first of all, strong mutual coupling boosts the transfer function tunability. And second, we can actually re-app these benefits of strong mutual coupling by formulating, calibrating, and efficiently using physics compliant models from multiport network theory. And the parameter estimation also led us to this virtual vector network analyzer concept. And finally, actually, a lot of these ideas directly apply to beyond diagonal tunability because we can have this diagonal perspective on beyond diagonal tunability. And with that, I'm happy to take questions.
Thank you so much, Philip, for the talk. Very interesting and clear as usual. Any question from the audience? Feel free to type in the chat or raise your hand. Okay, maybe I can start myself with a question. So actually, regarding the part one of your presentation, when you explored the impact of the mutual coupling strength into the transfer function tunability, so I was wondering if the results are consistent in line-of-sight channels and in channels where there is a rich multipath environment, or somehow the impact of mutual coupling depends on the multipath richness of the channel.
So we looked at this in the DMA context, where we assume the DMA is actually operated in free space and all the rich scattering happens within the dynamic metasurface antenna. But I think fundamentally the argument, the argument was basically related to saying, I mean, the intuitive argument is that the more the wave bounces around, the more sensitivity it accumulates. And so if rich scattering increases the number of encounters with the tunable components, I think it should increase the tunability.
Yeah.
Does that answer your question, or
Yeah.
was
Yeah, thank you. Yeah. I missed that you assumed, or maybe the experiment assuming free space propagation. So
yes.
Yeah, I guess if the multipath is more rich, then the observation should actually be stronger, right?
Sorry, a second. You expect then the benefit should be even stronger?
Yeah.
Possible. Yeah. We haven't thought about this, I guess, in the DMA context. For RIS, for sure. Yeah.
Yeah, thank you. Okay, maybe a second question still from my side. I'm very interested in the diagonal representation of BD-RIS, right? And so regarding the fixed circuit network, static parts of load circuits, so that can be characterized with a scattering matrix, if I'm not wrong, denoted as SLC, right? And in order to optimize your tunable load, you need the value of this scattering matrix. So if I'm not mistaken, in the paper you propose how to derive this matrix for a RIS having maybe a reduced number of ports. So I was wondering if there were some, this is an interesting problem, maybe if there are some analytical ways of getting that scattering matrix for any arbitrary, let's say, fully connected RIS, or
So my perspective on that problem is that actually, sort of from the experimental point of view, you don't even need to explicitly know that scattering matrix, because when you use the diagonal representation in an experiment, and this is what I did in the parameter estimation in this case, actually, and you apply the parameter estimation, you treat the two static components as just one big static system, and you estimate the scattering matrix, or an operationally equivalent proxy, for the cascade of the radio environment and the static components. And so you don't actually sort of need to explicitly separate out what parts are the radio environment, what parts are the static load circuit. Does that make
I
sense?
see, I see. Yeah, yeah, I completely agree. Yeah. So it will be kind of embedded into an equivalent channel, yeah, including the
Yes,
wireless part, but
exactly.
also
Yeah.
that network. Yeah. Yeah, I was just trying to think about this problem from a like theoretical signal processing perspective when you want to map all the contributions of all the part into the channel expression, right? But you're perfectly right. Yeah, it is actually maybe not needed in practice because of that reason. Yeah. Okay, we have a question in the chat. Pablo, do you want to read it yourself or I will go ahead?
Yeah, sure. Well, first, thank you very much for the talk. I think it's been quite interesting. I have a question regarding the beyond diagonal configuration you mentioned, because of course I understand that if you add some correlation between the loads or the tunable loads, at the end you're adding more degrees of freedom because you can make non-linear combination of these loads and so on, instead of just changing one of them. But the question is, at the end, you need, in the case of the DMA that you mentioned, you need to add more bias or anything else in the circuit to control this configuration. Otherwise, it is not configurable. So
Yeah.
what would happen if instead of adding more resources of more bit of controls to this correlation configuration, so to say, you add them directly to the reconfigurable elements? For example, adding more states to the radiating element or something like that. Have you checked this? If in this case you still have some benefit from the correlation in the loads instead of just adding these degrees of freedom directly to the element? Just a curiosity.
Yeah, I think this is a very good question. Actually, I think I don't know. I think this question in many ways is not specific to the beyond diagonal DMA, but it equally applies to BD-RIS. And I think it's actually something that has not been fully explored. You know, they're sort of when you the question is like how on what basis do you compare diagonal and beyond diagonal, right? Do you fix the number of either RIS elements or radiating meta-atoms in the DMA, or do you fix the number of tunable components? And in the BD-RIS literature, as far as I have seen, the usual approach was to say we have a fixed number of RIS elements, for example, because we have a fixed surface, and then uh, of course adding more tunable components via the beyond diagonal tunability improves the performance. But there has not been, as far as I know, much exploration of, well, what if the number of tunable elements is fixed? Then is it better to have a D-RIS with more elements or a BD-RIS? And that is, of course, the same question applies to BD-DMAs, and that is, I guess, the question that you asked, and we have not explored that so far.
Okay, thank you. Yes, because I was thinking, yeah, of course, I said DMA, but it applies to anything that is beyond diagonal. Because from a signal processing perspective or a communication perspective, I think that what may make sense is actually comparing in terms of bit of control. If I have, let's say, n bits of control to configure my system, how can I maximize the utility of these bits of control? Either adding them to the same number of radiating elements, but with more states, for example, changing pin diodes by varactors with 4 states or whatever. Either adding some correlation in the loads, or it's a mix of them. I think that's, I don't know, it's just a question that came to my mind after your talk. So it's just a curiosity whether you ask something about that.
Yeah, I think it's a very interesting question. I don't think I have a clear answer to it. I have some thoughts. Maybe from a practical perspective, uh, I think using varactors is fundamentally a lot more complicated than using pin diodes because you actually need ADCs in order to control them. So there might be some in practice, having comparing a varactor with a set of pin diodes might be complicated. But yeah, I think this point that in the correlations in the beyond diagonal representation, this is not something that has received a lot of attention in the theoretical literature, as far as I'm aware. And I think from a practical point of view, when you actually try to implement this, it's something that one has to confront. And that's why I think in practice, actually, the diagonal representation can be very, very helpful.
Okay, thanks a lot.
All right, thank you, Pablo, for the interesting question. Thank you, Philip. And I think this will conclude this this seminar. Let's thanks again the speaker, Philip, and see you in 2 weeks if you want for the third seminar of the series. Thank you all. Bye bye.